Hello, my name is Magnus Eide, and this is my Industry 4 system for controlling the air heater process. There are three main aspects to this implementation. One thing I focused a lot on was the ability to control multiple instances, here represented by having its own microcontroller. These controllers use MQTT to get their controller parameters. They also publish their temperature values and the output voltages to the MQTT broker. The MQTT broker is hosted on a local Raspberry Pi. The Pi also acts as an interface between MQTT and the SQL server. The interface is simply a Python script that subscribes to the MQTT topics and writes to the SQL server, as well as checking for updates in the SQL server and writing the data to the correct MQTT topic. Moving over to the online section of this diagram, there is an SQL database hosted in Azure and a web interface application using Python and Flask. Flask is a very popular web development framework for Python, which allowed me to reuse a lot of the code from the previously mentioned MQTT to SQL interface. Since the Flask application is hosted in Microsoft's cloud computing platform Azure, it can be accessed from anywhere in the world, allowing the users to control the process remotely. I will now go over the main aspects of each of the three applications and show how the SQL database was built. In the end, there will also be a small demonstration of how the system works. So let's start with the controller. It first includes some libraries, including the custom libraries for the PID controller, the low-pass filter, the air heater model for simulation, and in this case also a digital to analog converter. What's not shown here is that the application also uses an MQTT library, a JSON library, a Wi-Fi library for networking, and a network time protocol library. Both the digital to analog converter, the PID controller, the low-pass filter and the air heater model are initialized before the setup loop begins. First, the I/O pins are set as outputs or inputs before serial communication is initialized. Then it tries to connect to Wi-Fi, and when connected, it continues with connecting to the MQTT broker. The main loop begins with checking if Wi-Fi and MQTT communication is up and running, and if they're not, then it won't continue until it is. It then proceeds to run two functions at a different set interval. This is done to reduce the data traffic to the MQTT broker. The main cycle first reads the temperature either from the simulator or from the specified pin. The temperature value is then filtered using the low-pass filter, and if the controller is in automatic mode, a new output voltage is calculated by the PID controller. Some values are then printed to the serial bus before the heater voltage is applied to the pin. The MQTT communication is established with the reconnect MQTT function. It checks if the client is connected to a broker and tries to connect if it isn't. When a connection has been established using a Wi-Fi client, a username, and a password, the client is set to subscribe to 5 topics. The control topic is for retrieving manual controls for the heater and the fan. The PID topic is used for the PID parameters. The setpoint topic obviously is retrieving the setpoint. The auto mode topic is for setting the controller in automatic or manual mode, and the filter topic is for the alpha parameter in the low pass filter. If the client fails to connect, it will wait for 5 seconds before it tries again. If the client was already connected or established a connection, the callback function for the MQTT client is run. The callback function first reads the message received from the topic and tries to add it to the global JSON document, JSON-doc. If the value sensor ID in the message is the same as the device is given, the appropriate function for the topic received is executed. All the read functions are basically doing the same thing, checking for non-valid values and assigning the values to the global variables or object instances. In the main loop, the second cycle runs the write to MQTT function. This function simply takes the values that are to be sent to the MQTT topic into a JSON document and publishes the messages to the specified topic. If the controller is in automatic mode, it also publishes the output voltages to the control topic. That was mostly the controller. Now would be a good time to explain how the SQL database is built up. It consists of 5 tables, one for the output controls, here under the heater voltages and the fan voltages, one table for the temperature readings. These 2 tables are mainly populated by the controllers. In the middle, the device table contains all the device names and is used as a fortune key for all the other tables. The filter table, surprisingly enough, contains the alpha values for the low-pass filters for each controller, and the controller table contains the PID parameters for each controller, including the setpoint values. Now that we know how the MQTT data looks like, and how the SQL database look, I will now explain how the MQTT to SQL interface application works. This is the whole main loop for the interface application. It begins with establishing a connection to the MQTT broker and then steps into the loop. There it first checks for a connection to the SQL database and checks for changes in the tables. If there are changes in the SQL database, it publishes the last available data for each device in the device table. To reduce data traffic, a 1-second pause is added at the end. The checkDB for changes function reads the version from a change tracking implementation in the SQL database. Comparing this version to the last recorded version indicates a change, and the last control values from the database are fetched. This data is then published to the respective MQTT topics with the function publish changes to MQTT. It converts the data to JSON format and publishes the data to the respective topics, just like the controller application. The third and last application is the web user interface. This is a Flask application hosted on Azure and can therefore be accessed from mostly anywhere. The code itself is not so much to talk about, as it's mostly procedures from JavaScript. But one thing to mention is that it uses a somewhat different method of detecting change in the SQL database. The change detection is running in a separate thread from the Flask application and looks at the last recording in the tables to determine change. If a change is detected either from control values or from temperature readings, all the fields in the user interface are updated. Since this is a web application, this is done using WebSockets, allowing all clients to receive the change notification and updated values. The HTML script that defines the layout of the page, combined with the custom CSS style sheets, gives the following result. Here, the user can change the device to control and adjust the temperature set point with a slider. They can also fine-tune the PID controller and the low-pass filter using the buttons. Now I will demonstrate that the system is working. I will now open the user interface and serial monitor. If we have a look at the bottom section here, this is the MQTT to SQL interface. There is a lot of activity there, and that is basically because the temperature readings are updating every other second. To the upper left window, we have the serial monitor showing the output voltage, the current temperature, and the current set point. If I go into the user interface and adjust the set point, let's set it to 25 degrees. Close enough. We can see that it's already working to get there, and it's actually almost there. I can also change the PID gains. So if I add we can actually see it here. $3.9. Let's set it back because according to Ziegler, this should be 3. This should also be 3, but I found it unstable then. I can take this one way down. But yeah. And of course, we can also change the filter alpha value. But as you can see, the temperatures are very stable and they are very clean. And that is simply because this is a simulated system with no noise. There's no added noise in the simulator. But we can see that the web interface is actually controlling the set point and is updating through MQTT. Now, just to show the power of WebSockets, I have another user interface here. They are the same. As you can see, they update simultaneously. Come on, change. Okay, let's change the set point, then they will change. Yeah, as you can see, they update simultaneously. And the same goes for the other values. Now, I said that this is running in Azure. This is a cloud hosted web page, but that is actually a lie. As you can see, this is locally hosted. That is simply because in the Azure web page, WebSockets are a bit difficult to get to work. So as you can see, this is not updated, but if I manually update, then we get the correct values. So I can still change the set point from the cloud, 26.1, 26.1, but I don't get the updated temperature values in the online hosted web page. One of the biggest security risks in this implementation is that anyone with a URL can control the system. This can be solved by adding some kind of authentication to the web page before the user can access the controls. As for the machine-to-machine communication, both the MQTT broker and the SQL database is set up to require authentication. In addition, all remote communication to Azure has to follow the HTTPS protocol. This seems to be the reason for the malfunctioning of WebSockets. Overall, the system works, and it is possible that another WebSocket solution can be easier implemented to work with Azure's servers to solve the current problems.